Earth Science, Unit 3. In this lesson, we'll start off with our objectives. We'll talk about geothermal energy, solar energy, energy from moving water, energy from biomass, energy from the wind, and specifically we'll look at how hydroelectric facilities generate electricity, and we'll look at different types of tidal energy and how scientists feel that they can produce energy using the tides. Right now, most of that stuff is in the testing phases. We don't have very many large-scale tidal units actually producing electricity for us in our country. So our objectives, we're going to explain how geothermal energy may be used as a substitute for fossil fuels. We'll compare passive and active methods of harnessing energy, and we'll explain how water and wind can be harnessed to generate electricity. So renewable resources. Renewable resources are natural resources that can be replaced at the same rate in which we consume them. Some examples include using solar cells and collecting solar energy. Hydroelectric facilities, so generating electricity by the flow of water. Something that's starting to pop up in our area are wind turbines and harnessing the wind power that is generated through the flow of our atmosphere. And then we also have some geothermal energies that we collect, and we actively do this. Many homes are heated through geothermal units that basically take heat energy from inside of the planet and we use them inside of our homes to heat our homes. Now it's important to realize that in the United States this isn't a huge energy source, but in other countries geothermal energy is a very big deal. So geothermal energy. It is the energy that's produced from the heat within our planet. The resulting steam from water passing by nearby magma chambers or hot gases that are coming off of magma chambers. Those magma chambers or gas chambers are deep within the earth, and they give us large amounts of heat energy. The picture that you see here is a picture of pipes in parts of Iceland. Iceland has a great deal of geothermal energy, and they actually supply the entire country with heated water or steam water, and these pipes kind of run all over the country, supplying different buildings with hot water. So engineers and scientists have harnessed geothermal energy by drilling wells to reach the hot water. Again, another picture of pipes that are pumping water, heated water to different areas. The steam and hot water are used as a source of heat, and they also are used to drive turbines. So turbine spins, generating electrical energy. That electrical energy is then pumped out to houses through electrical lines. Solar energy. Solar energy is the energy that is received by our planet from the sun, and it is in form of radiation. Specifically, that energy comes in the electromagnetic spectrum. Solar energy can be converted to heat, and in many different ways we can then use that energy to supply electricity, to heat our homes, to even boil water and different things like that. There are two systems that are involved in heating, a passive system and an active system. In a passive system, we really just have building materials that are heated. Those building materials are heated just by the sun. They aren't created to absorb solar energy, but they just do. Many things on our planet absorb solar energy. You've probably seen passive systems in action before. Probably when you're a real young kid, you hear those creaks and groans that occur inside of the house, specifically in the morning and in the evening. Those creaks and groans occur due to the expansion and contraction of building materials, specifically wood. So as material is heated up, it expands. As it cools down, it contracts. So a lot of times, as you're ending up with solar energy hitting your building materials, those building materials are going to gain that solar energy. The building itself is going to slowly heat up. This picture right here shows a thermal image of a house, and so it says that the atmospheric temperature for that day was 84.2 degrees, but you'll notice different parts of the house have temperatures that are much greater. So right here in the shade where the tree's protecting the house, we have 82.7 degrees. Over here where the sun is hitting the shingles, we got 154.1 or 162.3 degrees Fahrenheit. So many building materials, as they absorb solar energy, are going to increase in temperature. An active system, on the other hand, is a system that uses solar collectors that are specifically designed to collect energy from the sun. Specifically, we call those photovoltaic cells. So we are collecting or we are converting solar energy into electricity. You've probably seen these. They're becoming pretty popular along roadways, especially in our UP, where it's a little bit more difficult to send electrical lines to some of those areas where not too many people live. So what they do is they put one of these photovoltaic cells out on signs that maybe are supposed to flash, or lights that are supposed to flash, and the energy that is supplied to that sign strictly comes from solar energy. Energy from biomass. Biomass is any plant material, manure, or other organic matter that is used as an energy source. It is a major source of energy in many developing countries. Specifically manure. Manure is actually burned inside of homes in order to heat homes. We also use some of these biomasses or these biofuels, and specifically we can have bacteria that decompose the organic matter and they produce gases like methane, and we burn methane inside of homes or get tanks of methane to help in some trade industries. Liquid fuels such as ethanol also form from the action of bacteria on biomass. So we create ethanol through the bacteria breaking down corn products, and those bacteria basically release different forms of ethanol, and this process can actually create the energy that we burn inside of cars. More than half of all the trees that we cut down are used for fuel for heating or cooking. Many of you may have started to hear of biomass stoves. I actually just put one of those in my house. It's basically a heating unit that will take things like corn or cherry pits or wood pellets or a number of other things, and it will burn them in order to produce heat. So the majority of our biomass is actually used not for building materials, but it's actually used for the production of energy in the form of heat. So quick quiz. Name 3 sources of renewable energy. So we've talked about 3 of them so far. Name those 3. The 3 are geothermal, solar. Those 2 we've talked about. You could have said hydroelectric, and then also biomass is the other one that we've talked about so far. Energy from the wind. Wind energy is now being used to produce electricity in locations that have constant winds. These are probably familiar to us. We have a number of them that are going up around the Ithaca and Breckenridge area, and at some point there's supposed to be some that go up between Carson City and our school here, but it's definitely something that is becoming more and more popular. Wind farms may have hundreds of giant wind turbines that can produce enough energy to meet the electrical needs of entire communities. Much of the energy that is being produced right now within the Breckenridge and Ithaca area is actually being transferred elsewhere. The downfall to these energy farms is that we haven't found a very good way for storing the energy that is produced. The wind doesn't always blow on a daily basis at a constant rate, so we need to find some way to store that energy for later use, because we don't necessarily always use our electricity during windstorms or during high wind periods. High wind period might happen at midnight when most people are not using electricity at all in their homes. So continuing on with that point that I just made, this bullet just simply says wind generators are not practical everywhere because the wind does not always blow. Wind energy cannot be depended on as an energy source for every location. Now in Michigan, we have found that there are some areas that do have a constant amount of wind energy that we can harness. This picture right here shows some of the areas where there is a higher wind speed. You'll notice on the Plain States, just to the east of the Rocky Mountains, there is a pretty moderate wind pattern. In parts of the Rocky Mountains, there's very high wind patterns. And then as we get over towards the east, it kind of goes down a little bit. This actually shows Michigan as being very low. I would say we're probably more in the moderate range. We're starting to find that we're more in the moderate range, at least in the central Michigan area. But then right along the lakeshore, there's pretty high amounts of wind right along there as well, due to the temperature difference between the lakes and the land. So we get kind of a sea breeze, land breeze going on there due to those temperature differences. Hydroelectric energy. Hydroelectric energy is electrical energy that is produced through the moving of water. So rivers and streams flow. For a very long time, we actually produced different types of energy, or used the energy of streams and rivers to produce different things. This dam right here is the Croton Dam. It is found over by Newaygo. Many of you maybe even know of this or have fished there. This area is pretty popular among anglers and fishermen, but it's an area where the Muskegon River is impounded. There is an electric facility that sits right on the Muskegon River. Water is released in this area if the water levels get too high, but this area over here is the actual hydroelectric facility. So moving water is one of the oldest sources of energy. It can be harnessed from the running of water from rivers and streams, and we can also harness the ocean tides and the flow of water that occurs there and generate electricity. Today, 11 to 16% of the electricity in the United States comes from hydroelectric power plants. At our hydroelectric plant, massive dams hold back running water and channel the water through the plant. Inside the plant, the water spins turbines, which generate electricity. So you can see in this picture here, right here is where the reservoir would be. The dam is created. This is called a penstock, and there's usually an intake that is gated off in some way so that you aren't getting fish or other things that end up all the way down inside of the turbines. But water just basically flows down this penstock, comes in contact with the turbine, spins the turbine. Excess water is just then sent right out into the river below. But as the turbine spins, it produces electricity in the generator, and then the generator pumps electrical energy out to any power lines that supply homes with the electricity that they need. How a hydroelectric dam generates electricity. This diagram is kind of the same thing that was just talked about, just a little bit more in depth. So again, the reservoir is here, penstock. The penstock allows the flow of water down to the turbines. You can see a little more specifically what the turbine looks like. So the flow of water comes down, catches some fins that are off of that turbine, causes a spinning motion. Extra water is discharged. That spinning motion then is used in the generator to produce electricity. Tidal energy. And this is kind of an interesting one because it uses quite a bit of engineering and modern ingenuity in order to create the electricity through this process. So it's a largely untapped future resource. We are just currently starting to explore it. It is a resource that could use the world's oceans to generate electricity. So obviously we have large oceans all over the entire world. This would be energy that would be supplied to the masses of the world. It uses pressure from tides to turn turbines to create electrical energy. Wave energy is another future resource that we are currently looking into. The use of turbines or buoys with magnetic coils and hydraulic arms. Those magnetic coils and hydraulic arms are used to generate electrical current as those devices bob up and down in waves. So both tidal energy and wave energy are kind of the energies of the future. These pictures show a number of the different experimental types of facilities that we are creating. So you can see right here, we've got kind of this big tidal energy one where we've got currents in the ocean. This device right here is lowered right down into the ocean, where as the current runs past it, the turbine in the center spins. Same thing over here. These are just set right on the bottom. So they're basically kind of like the large wind turbines that you see north and east of the school, and basically they're just put inside of the ocean, where as water flows past them they spin. Down here you can see some of the wave energy facilities, or the wave energy experimental stations. So these devices right here, as the waves go up and down, they bend and move. As they bend and move, pressure is created in some hydraulic arms. That pressure can then be used to turn turbines and generate electricity. Same thing goes with this one right here. These are wave generated ones that as the wave goes up and down, it causes the top part here to move up and down, and then the hydraulics produce pressure as well. These right here are kind of along the same aspect of these. Instead, as the wave goes up and down in these though, this device right here just slides up and down inside the frame, and again it produces pressure due to hydraulics.
Tidal energy, energy generated from the movement of tides, is an excellent alternative source of energy in areas where the coastline has shallow, narrow channels. As the tide rises, water enters a bay behind a dam. The gate then closes at high tide. The gate remains closed as the tide lowers. At low tide, the gate opens, and the water rushes through the dam, moving the turbines, which in turn create electricity.
I'm going to play the video one more time so you can see the process that is involved in it.
Tidal energy, energy generated from the movement of tides, is an excellent alternative source of energy in areas where the coastline has shallow, narrow channels. As the tide rises, water enters a bay behind a dam. The gate then closes at high tide. The gate remains closed as the tide lowers. At low tide, the gate opens, and the water rushes through the dam, moving the turbines, which in turn create electricity.
One downfall to this process is that it's not going to be practical for everywhere. You're going to have bays or inlets that are blocked off with this type of facility, where you have tides that are actively moving in and out. And then the timing aspect of it's kind of a problem as well, because the tide doesn't happen as regularly as what we produce electricity or use electricity. So we're going to have to find some different solutions to some of the problems that are faced with these tidal energy facilities, and the geography around areas and how the geography will actually affect creating these types of things. Cycles on our planet. We're going to talk about a number of cycles that occur on our planet. We are very familiar with the nitrogen cycle currently. We've done quite a bit of different things with the nitrogen cycle inside of our fish tank. So nitrogen cycle will be kind of a little bit of review. The carbon cycle, slightly review, and the water cycle will be quite a bit review. So a cycle is a group of processes in which matter and energy repeatedly move through a series of reservoirs. A reservoir is a place where matter or energy is stored. Many elements on Earth cycle between reservoirs. These cycles rely on energy sources to drive them. Many times the energy source that we're talking about is the sun, but not always. The length of time the energy or matter spends in a reservoir can vary from a few hours to several million years.
A biogeochemical cycle is a process by which materials necessary for life are circulated through the environment. One biogeochemical cycle is the water cycle. In the water cycle, water cycles between bodies of water, the atmosphere, precipitation, and groundwater. Another biogeochemical cycle is the carbon cycle. Carbon is used by photosynthesizing plants, algae, and bacteria to build organic molecules. The carbon passes through living things until it is returned to the environment through cellular respiration, combustion, or death and decomposition. The nitrogen cycle is another biogeochemical cycle. Bacteria called nitrogen-fixing bacteria are able to use atmospheric nitrogen to produce ammonia. Other organisms can then use the ammonia as a nitrogen source. The nitrogen is returned to the atmosphere by denitrifying bacteria.
So the nitrogen cycle. In the nitrogen cycle, nitrogen moves from the air to soil, from plants, and then into animals. And then it also removes back into the air again through the process of decomposition. Nitrogen is removed from the air mainly by the action of nitrogen-fixing bacteria in the soil. The nitrogen enters plants, which are eaten by animals. The nitrogen is returned to the soil by the decay of any materials as they're breaking down by bacteria, and also that it is released through animal wastes. Chemical processes that occur in the soil then release the nitrogen back into the air. So the picture illustrates the nitrogen cycle. We should be fairly familiar with the nitrogen cycle. Nitrogen-fixing bacteria in the soil and root nodules produce ammonia, NH3, so taking atmospheric nitrogen, putting it into the soil. Ammonia is NH3. Again, we measure that inside of our fish tank. We can have denitrifying bacteria that then take the nitrogen that is found in the soil that is probably placed there through decomposition, break it down, turn it back into N2, so atmospheric nitrogen. Runoff can put some of that inside of plants, some of the different nitrogen, specifically ammonia, inside of lakes and streams, and then those organisms, aquatic plants that are found there, can absorb them. Bacteria in the soil add water, bacteria in the soil and water add nitrogen to the atmosphere. And then also one more thing, lightning can actually convert some atmospheric nitrogen into nitrates that organisms can use. So again, we measure nitrates inside of our fish tank. This illustration shows kind of the same process, a little bit different of a rendition to it. So ammonia, nitrites. After we produce ammonia, nitrification creates nitrites. Remember, nitrites in much of any form are not going to be very good for our fish at all. But then nitrites can continue through nitrification and they can create nitrates, which are not nearly as harmful to our fish as the nitrites. But then plants absorb them, and then the cow comes along and eats the plant. Those nitrates are absorbed into the cow, and we eat the cow, and we take in those nitrates. Or denitrification can occur, and those nitrates are just converted back into nitrogen gas found in the atmosphere. So quick quiz. Identify 2 nitrogen reservoirs on Earth. Remember, a reservoir is a place where matter or energy is housed. Answers will include 2 of the following: the atmosphere, animals, soil, and plants. Any of those places we may find nitrogen within those things. Carbon cycle. Carbon moves through all 4 spheres through the carbon cycle. In the short-term carbon cycle, plants convert carbon dioxide, CO2, from the atmosphere into carbohydrates. When organisms' bodies break down the carbohydrates and release some of the carbon back into the air as CO2, or through their organic wastes as CO2 or methane, CH4. So short-term carbon cycle is organism eats the plant and releases carbon dioxide into the atmosphere. The carbon dioxide is used by the plant and incorporated back into the plant. That's the short-term carbon cycle. The long-term carbon cycle, it stores carbon in the geosphere in a type of rock called a carbonate. So it's much longer term. It happens much quicker, or it doesn't happen nearly as quick as the short-term carbon cycle. So the figure right here, it represents the carbon cycle. So we'll start up here in the atmosphere with carbon dioxide. Carbon dioxide can be dissolved inside of water. So many of our oceans are absorbing carbon dioxide. Photosynthesis takes that carbon in and creates the plant structures that we have. And then organisms eat the plants and we eat the organisms, so on and so forth. If we burn those plants or we go through respiration, the carbon dioxide ends up back in the atmosphere. Some plants may die and animals die, and it creates plant remains, like layers of plant remains. Then it's going to store that carbon in the geosphere, and again, those rocks are called carbonates. Natural gas can be produced through this. Oil can be produced through this process. Coal. Limestone is produced through this process. As those rocks eventually end up at the surface, erosion can occur, and we go back into carbon dioxide being absorbed inside of the water. Or we can go through respiration and decomposition, releasing that carbon dioxide back into the atmosphere. Or just simply bodies of water can give off carbon dioxide back into the atmosphere. So a pretty complex cycle is going on with the carbon cycle. Phosphorus cycle. During the phosphorus cycle, phosphorus moves through every sphere except the atmosphere. Phosphorus enters the soil and water when rock breaks down. When phosphorus in the rock dissolves in water, or when organisms excrete phosphorus in their wastes. Plants absorb phosphorus through their roots and incorporate the phosphorus into their tissues. Animals absorb phosphorus when they eat the plants. When the animal dies, the phosphorus is returned into the environment through decomposition. This picture shows the phosphorus cycle. So I'm not going to go in great detail with the phosphorus cycle. It's not anything that we're going to spend a whole ton of time on. But it definitely supplies our environment with a lot of the nutrients that are needed for plants to grow. The water cycle. This should be review. The movement of water from the atmosphere to Earth's surface and back to the atmosphere is called the water cycle. In the water cycle, water changes from liquid water to water vapor through the energy transfers involved in evaporation and transpiration. During these processes, water absorbs heat and changes into a gaseous state. That process is called evaporation. When the water loses energy, it condenses to form water droplets, such as those that form clouds and fall to Earth's surface as precipitation. We're probably familiar with seeing condensation on the side of our cold pop can during the summer, or even our fish tank. As we had warmer temperatures in the fall, and as we get to warmer temperatures in the spring, we'll notice a lot more condensation on the outside of that fish tank because the fish tank is very cold with the chiller operating. As warmer air masses move in, the water droplets that are evaporated inside of the atmosphere are going to condense on the outside of that cold tank. This figure represents the water cycle. It's a little more complex than the one that popped up on the last screen, but we've got evaporation and transpiration adding water to the atmosphere. As condensation occurs, clouds and water vapor kind of condense or form, and then precipitation can occur, both as rain or even as snow over here. As these things hit the surface, we get surface runoff. That water may end up in the groundwater supply. It may just end up running out to a stream or a local lake, where that process can just start all the way over again. Plants might absorb the water and then go through transpiration, or it may end up just going through the process of evaporation again.